So today I'm going to continue on electrostatics and magnetostatics. What we have was that we have previously discussed Maxwell's equations. I don't know why we went to that one. Curl of E is minus dB dt, and then we have curl of H is dd dt plus J, which is generalized Ampere's law. We have divergence of B equal to rho, divergence of B equal to 0. And then for statics, we're going to assume that partial T equal to 0. Okay, and for electrostatics, then we have just if we have partial T equal to 0, this term goes to 0, this term goes to 0. For electrostatics, then we have just curl of E equal to 0. And the other equations that involves electric field is the electric flux equation, which is Gauss law for electric flux. And then you can solve this equation by assuming that E is equal to minus grad phi, okay, because we know that divergence of grad phi is equal to 0. So if we assume that E is equal to minus grad phi, this equation is automatically satisfied. Then D is epsilon E would be just minus epsilon grad phi, and we can plug this equation into here, then we get divergence of epsilon gradient of phi equal to rho. Okay, this equation usually can be solvable if epsilon is a constant. Then you can take the epsilon outside, and this equation becomes divergence of gradient of phi is equal to minus rho over epsilon. Okay, so there's a minus sign that I'm missing here. There's a minus sign that I'm missing here. So this is called Poisson's equation. Okay, this is called Poisson's equation. And then we have the other magnetostatic equation. We have the case when, say, let me put on auto save, then maybe it would just save onto the thing. Okay, I think it will automatically save my slides. Then we go to the next case, which is the magnetostatic case. In that case, we will just look at the four Maxwell's equation previously and see which one has something to do with magnetic field. So these two equations have something to do with magnetic field. So if we look at the magnetostatic case, Ampere's law becomes just this. And then we have Gauss law for flux or magnetic flux is equal to that. Then the question is, the next question to ask is, how do we solve this equation? Well, there is a identity that we can use is that if you assume that B is equal to curl of A, okay, and using the fact that divergence of B then is equal to divergence of the curl of A, and this is equal to 0. So if you assume that B is equal to curl of A, this equation is automatically satisfied. If that equation is automatically satisfied, then we only have a second equation to solve. Okay, let's look at why this is always equal to 0. And one way to remember that is that we know that A dot A cross B is always equal to 0. If we take a vector B and crossing with A, and then dotting with A again, you can show this to be 0 by geometrical argument, because this will give you something that's orthogonal to A, and dot with A again is equal to 0. You can also show it algebraically. by expanding A and B in terms of Cartesian components, and then showed by algebra that it goes to 0. And you can use the algebra derivation that you have here to prove that this in fact is equal to 0. So it's very much for the same reason that this is equal to 0, that we have that equal to 0. Okay? So then how do we solve this equation? Then we have yet this equation to solve. So since B equals mu H, or H equals to B over mu, we can substitute H into that equation to get curl of B over mu is equal to J, and this implies the curl of 1 over mu curl of A equal to J. Okay? So this is one equation that we arrive at. However, to make things simpler, we assume that mu is constant, a constant independent of position. Then we can take this mu outside, and if you take the mu outside, then you have curl of A, and this is 1 over mu that you have taken outside. Then when you put it back on the right hand side, it just becomes mu J. Okay? So how do we solve this equation now? It's a little bit more complicated with curl of A compared to the Poisson's equation. We have double curl, and what we can do is to make use of the identity that curl of A equal to the gradient of the divergence of A minus Laplacian of A. And this identity is actually same as the back of the cap formula. Okay, A cross B cross C is equal to B A dot C minus C A dot B. This is for good mnemonics known as the back of the cap formula, and if you apply that formula to this equation, you get what we have on the right hand side. Again, this equation can be proved by algebra. You can prove by geometrical arguments, or you can prove by algebra. That is, you plug A, B, C with the Cartesian components, and then you get the right hand side. You can use the same algebra to prove this identity over here. Okay? So we are going to make one more thing to make things simpler, which is to assume that divergence of A equal to 0. Okay? This is usually called gauge, called a Coulomb's gauge. And if you assume Coulomb's gauge, then this goes to 0. Okay? What you have on the left hand side is then Laplacian of A equals to mu J. Okay, the Laplacian is the shorthand for del dot del. Del dot del is equal to the Laplacian. If you work this out, then it's actually x partial x plus y partial y plus z partial z dotting with itself plus y partial y plus z partial z. Okay, and you work out the Laplacian properly, you find that the Laplacian is just equal to partial squared partial x squared plus partial squared partial y squared plus partial squared partial z squared in Cartesian coordinates. Okay, so then our duty then reduces to solving this equation. Laplacian of A equals to minus mu J. Okay, if you look at what we had from the previous slide, let me blow this up bigger so they can see that. Okay, if you look at what we have, we start out with this equation over here. Can you see my cursor?
Yes,
hello?
we can.
Okay, you start out with this equation. After you go through the manipulation, you end up with this equation. This equation is nothing but very similar to 3 Poisson's equation. Okay, we have Poisson's equation over here, and this is the vector equation. You have A, which is the vector, J, which is the vector, and so on. And you can think of it as three scalar equations if you want to. You have three scalar equations that can write out each component. For instance, I can write out the x component to be this, and then you can similarly do it for the y component. Is good. Sorry, this should be jx, and then this should be jy, and then we have minus mu jz. So you actually have three scalar Laplacian equations to solve concurrently, and we know how to solve each of them before. Okay, previously we already learned how to solve an equation that's very similar, which is the Poisson's equation. Okay, so now we have a vector Poisson equation. This is vector Poisson equation. Okay, since we know how to solve each component before using the Green's function, so what we do then is to say that ax r is equal to mu over 4 pi dv prime j of r prime. Sorry, not j of r prime, it should be j sub x of r prime, r minus r prime. Okay, this is just a use of the solution that we had in solving the Poisson's equation. We just apply it to the x component. We have this, and then you apply it to the y component and the z component, and after you have done that, you can collect them all together and say the vector component of A is just the sum of, this is the volume, okay, this is the volume integral jx plus jy plus jz, then it is equal to that. Okay, and so that dv is a volume integral, is dx prime dy prime dz prime. Okay, so are there any questions so far as to how we solve this vector Poisson equation? Given this vector Poisson equation, we use our prior knowledge of solving the scalar Poisson equation, and then we just apply the knowledge component-wise, component by component. Then we have this this solution written in this manner. Any questions on this?
Yeah, I had a quick question.
Okay, sure.
What physical quantity does A represent?
Well, A is something that has been debated for a long time. That at this point, you just have to know that the curl of A is equal to B. You just have to know this fact. Okay, curl of A equals to B, and some people like to liken it to some kind of a momentum, electromagnetic momentum of some sort. It's not directly the magnetic flux, but the curl of this momentum field is equal to the magnetic flux. But you can think of it as being equal to just some kind of electromagnetic momentum. Okay, is that good enough answer, or you want to know more?
Yeah, that's good. Thank you.
Okay, so you can think of it as a momentum of some sort, but I like to talk about the Coulomb's gauge more. Coulomb's gauge, we say that B equal to curl of A, and then divergence of A equal to 0. This is Coulomb's gauge. Okay, so this is like the statement that says that if I have an A prime is equal to A minus grad psi, okay, and if I take the curl on both sides, if I take the curl of both equations, then I will get curl of A prime is equal to curl of A, because curl of the gradient of psi is equal to 0. You can see that A is not unique. A is not unique. A is not unique if we just stipulate what its curl should be. Okay, if we just stipulate the curl of A equal to B, you always can add a term to A and make a new A prime, and the curl of A prime would be the same as curl of A. So okay, A is not unique, and in order to make A unique, what we need to do is actually to add the additional fact that divergence of A has to be equal to 0. Okay, so this is very much like saying that if I have a vector A, and if I just cross it with B and tell you what C is, stipulating the curl of A with respect to a vector B and telling you what it is not enough. What you need to do is that you have to take B and dot with A and get the scalar S. You have to do both this. Okay, then the vector A can be uniquely determined. You can think about it yourself. Say if I have a vector A and B is any constant vector that is pointing in that direction, and if I just stipulate the fact that A cross B is equal to C, a vector say pointing in the out of the blackboard or on the paper, there are many vector A, many vector A that can cross with B and points in the same C direction. Okay, so in order to make vector A unique, you also have to stipulate what the dot product of A with B is. You have to take the dot product of A with B and stipulate what the angle is. Okay, and if you stipulate what the dot product, you essentially stipulate this angle. Otherwise, A can be any vector pointing in any direction, and this angle is not stipulated. Okay, that's the essential meaning of the Coulomb's gauge. Okay, and then you will show that the phi that you have, the phi that I have from this equation, the previous equation, you can show that it should be 0. It satisfies this equation, and if you have the condition that phi tends to 0 when r tends to infinity, then the only solution that you have in this equation is that phi has to be 0. Okay, that is the only solution that you can have. I would not be able to prove to you, but this is a fact, and it can follow from this Earnshaw theorem. It is stated more elaborately in the lecture notes, but I would not belabor the point over here. Okay, are there any questions so far? If not, I'd like to move on to a new topic. Okay, I'd like to move on to a new topic, okay, which is on boundary conditions. Well, we have seen that in statics, we have two equations, electrostatics. We arrive at a Poisson's equation, okay, that looks something like this. Okay, and then we arrive at for magnetostatics, we arrive at something that says that Laplacian of A is equal to minus mu J. Okay, these are called PDEs. These are called PDEs, or partial differential equations. Okay, they're called partial differential equations, and they can be solved in practice. But in order to solve them, you need to provide boundary conditions for the field. And hence, having the PDEs alone is not enough to solve this equation. You need to provide boundary conditions. And you have to say solve this problem in a certain domain like phi, and then you have to tell us what value does phi have at the boundary of this domain. Okay, so let's look at boundary conditions, and let's look at Laplace's equation more closely, or Poisson's equation more closely. Let's assume that it's 1D, one-dimensional to be simple. Okay, let's assume that it is one dimension to be simple. Let's assume that epsilon is not a constant, but epsilon is a function of x. And epsilon has something that looks like this. It's a constant in this region 1. Okay. And then at the place where x equal to x naught, there's a jump discontinuity in epsilon of x. And then we ask ourselves, if we solve the problem for phi 1 and phi 2 in these two domains, and this is region 1 or domain 1, and then this is region 2, okay, and we can quite easily obtain the solutions in region 1 and region 2, but we have to solve them together using boundary conditions. So let's address the issue of what the boundary condition should be. Okay. Let's assume that we have Laplace's equation. Epsilon phi, or Poisson's equation. Let's assume that the problem is divided into region 1 and region 2, and the problem has epsilon 1 and epsilon 2 in these two regions. Let's assume that we have a charge, rho, as a function of x, and rho as a function of x is a delta function in x. At the position x and equal to x naught, there's a delta function here. This represents a surface charge density. Okay, let's assume this is wrong, sorry. Epsilon gradient d. And we can write down this equation in one dimension. This can be written as partial x, epsilon as a function of x, partial x, phi, which is function of x, is equal to minus rho, which is a function of x, and is minus rho naught, delta x minus x naught. Okay? And we like to ask ourselves, what kind of boundary condition does B satisfy at that interface over there? Right hand side, we have a delta function singularity. Okay, so on the left hand side, a singularity must emerge. The singularity must emerge, which means that this function here must be jump discontinuous. I'd like to introduce you with the notion that if a function has a slope discontinuity, if you differentiate it, you're going to get something positive. Maybe something, if you differentiate it, it will go something like this. Let me see. It will go something like this, okay? If you apply d dx to this function, it has to have a step discontinuity. A function with slope discontinuity when differentiated gives you step discontinuity. However, a function with step discontinuity, like this over here, okay, this function, if you were to differentiate this function, you will get something positive on the left-hand side, and then it would jump to 0. Okay, jump to 0. But then in between something happens because there's this differentiation of something that has infinitely large slope. Okay, so what you have is that you will have a delta function singularity. Can you see that? So if you differentiate a function with step discontinuity, you will get the delta function singularity. I think this you might have learned from electrical engineering courses. Okay, so if you look at this equation now, on the right hand side we have a delta function singularity. What it says is that this function in the integrand here, in the derivative here, must have a step discontinuity. Okay, otherwise this equation cannot be satisfied because I have a delta function singularity on the right hand side. The function that I have just circled has to have a step discontinuity. And the mathematical way of showing this is actually to integrate this equation between, say if I have this equation, I write it again over here, epsilon x d dx phi of x, okay, is equal to minus rho naught delta x minus x naught. I integrate this equation from x naught to minus delta to x naught plus delta. Okay, I integrate that equation from a point that is slightly, I have this delta x minus x naught here, this is x naught. I'm going to integrate it from a point that is slightly to the left, which is x naught minus delta, to a point that is x naught plus delta. Okay, and then on the right hand side I'll do the same. Rho naught is a constant, so when I integrate from x naught minus delta to x naught plus delta dx, I will have that on the right hand side. But on the left hand side, when I integrate that thing is an exact derivative. So on the left hand side I will have epsilon of x d dx phi of x, and then evaluated at x naught minus delta, x naught plus delta, because there's a range that I integrate over. Okay, left hand side equals this. And the right hand side, because it's a delta function, what should I get on the right hand side? If I integrate over an interval that captures where the delta function is, what should I have on the right hand side? Anybody? Anybody wants to volunteer an answer? What should I get on the right hand side? Here I'm just seeking the area under the delta function. What is the area under the delta function?
Should be 1.
Very good. It just should be 1. Okay, I have just 1 on the right hand side. Okay, so what I have then is that I evaluate the left hand side. Okay, and it was that jump discontinuity that contributes to the delta function on the right hand side. So if I evaluate the left hand side, I can write as epsilon x plus d dx phi of x plus minus epsilon x minus d dx of phi of x minus. That is when I evaluate this at the two endpoints where I define x plus to be x plus delta, x minus to be equal to x minus delta, in the limit when delta goes to 0. Okay, I define those x plus and x minus to be that, and that should be equal to rho naught. Okay, that should be equal to my rho naught, and then what happens then is that let me see. How do I close this? How do I close this right-hand column? Well, how do I close this right-hand column? Does anybody know? Can you help me out with closing the right-hand window? It just pops up and I don't know how to get it to close. It went away. Okay, it went away after a while. Okay, thank goodness. Okay, so I have the boundary condition that epsilon x plus d dx of phi of x plus minus epsilon x minus d dx of phi x minus is equal to minus rho 0. There should be a minus here, I think. And there should be a minus sign. Right. But what is d dx? d dx phi is equal to minus e sub x, because we define e to be minus gradient of phi. So this equation can also be written in terms of electric field. So it will be minus epsilon x plus dx x plus minus, or plus now, epsilon x minus dx x minus is equal to rho. Rho naught is the amplitude of the current sheet that we have at the interface. Okay, the amplitude of the current sheet. So this boundary condition is nothing but the fact that this is just d of x plus d x of x minus is equal to rho naught. Okay, and this is the usual boundary condition that dx x plus minus dx x minus is equal to rho naught. Okay, this is the surface charge density. Any questions so far? If not, then let's move on to the next topic. Okay, which is that let's look at the boundary condition from Faraday's law. This is the boundary condition from Poisson's equation. Okay, Poisson's equation follows from the divergence of d equal to 0 equation. Okay, and let's see if we were to look at some other boundary conditions, like Faraday's law. What kind of boundary condition follows from Faraday's law? Faraday's law says curl of E is equal to minus dB dt. Okay, as we said before, the boundary conditions are given by matching singularities. In this equation, if everything is regular and finite, what it means is that there's no singularity on the right-hand side. There's no singularity on the right-hand side, which means that there couldn't be any jump discontinuity on the left-hand side. Okay, curl of E has to be something that produces no singularities. Okay, so what we have is the fact that if d dx of f of x is finite, f of x is continuous. Okay, so this is something that you can learn from your mathematics. that if f of x is a continuous function, if we differentiate it, you cannot have a jump discontinuous. So if f of x looks something like this, continuous, if you were to differentiate this function, it cannot give you something that's infinitely large. So we can see this more by very carefully looking at curl of E. Curl of E, you can write it out at Cartesian coordinate. We can actually take a boundary and impose a kind of a local coordinate system. You can call this y hat. You can call this x hat, for instance. Okay, x hat is our normal component. Y hat is a normal component, and x hat is the tangential component. And we can use the local coordinate system to write out curl of E. Curl of E can be written as y partial y cross with E. Okay, E can be written as x ex plus y ey plus z ez. But we are looking at this problem in 2 dimensions so that we can ignore the partial z derivative, and if you work this out carefully by taking the cross product, you will get something like z partial x ey minus y hat partial x ez. Okay, we multiply out term by term, and that's what you have, and then you will have z partial y ex plus x hat partial, nope, this is no good, plus x hat partial y ez. Okay, and then since the right hand side is finite, what it says is that if this is my y derivative, what I have is that the y derivative must be finite. Okay? If I look for change in the y direction, this derivative must be finite, and if they are finite, if the y derivative is finite, what it says is that E1z must be equal to E2z at interface. Okay, and E1x must be equal to E2x. Okay, if these derivatives are finite, let me write this properly. Okay, if these derivatives are finite, it says that they must be continuous. They must be continuous, meaning that the field components must be continuous. Okay, so if you work this out properly, what this is that E1z and E2z are actually the tangential component of the electric field x, y, z. Z is pointing out of the blackboard. So if you look at the local coordinate system, what it means is that n cross E1 is equal to n cross E2. Okay, you can look at the other components and figure this out to be true. I would have this written out more elaborately in the lecture notes so you can read it more carefully. But the important thing to notice is that since the right hand side is finite, curl of E must be finite. If curl of E is finite, E must be continuous. If E must be a continuous function, tangential E must be continuous. Okay, so this says that tangential E continuous. Okay, so that is Faraday's law. And then we can go with Gauss law for electric flux. Okay, Gauss law for electric flux. Okay, which is this one over here. Again, if you put a surface charge density at this surface such that there is a singularity there, and if the surface charge density is such that it's infinitely dense at this surface, okay, then you can show that in fact you will have a charge discontinuity. We can put again a local coordinate system z hat equals to n hat, and then we can again put the x hat equal to t1 hat, and then you can have y hat, which is coming out of the paper, t2 hat, and then you can write your divergence of D in Cartesian coordinate using this local coordinate system to be partial x dx plus partial y dy plus partial z dz is equal to rho. Okay? But if rho is finite, then I know that dx, dy, dz must be continuous. However, if rho is not finite, and if I express it using the local coordinate system, it is a delta function singularity looking like this. This means that it is a surface charge density. Okay, it is a surface charge density, which means that I have a delta function singularity on the right hand side. There must be something from the left hand side that produces the same singularity. This is called singularity matching. This is called singularity matching. So if I have a delta function as a function of z on the right hand side, which of the three terms would give me a delta function singularity? Now, with the intuitive understanding that if I differentiate a function with a step discontinuity, I get a delta function. If I differentiate a function with a slope discontinuity, I only get a step discontinuity. Okay? If I, of course, differentiate a function that's very smooth, I don't get any discontinuity at all. So of these three terms, I have a delta function of z on the right hand side. Which of them would give me a delta function of z, do you think? Anybody wants to volunteer an answer? I have three terms on the left hand side. I'm going to differentiate them. And I'm going to get a delta function of z on the right hand side that represents a surface charge density, which is very, very dense at z equal to 0. Okay? Of these three terms, on the left hand side that I differentiate, which of them has the potential of giving me this delta function singularity? Anybody?
This should be the z term.
Very good. It should be this term. Very good. Excellent. Okay. This is the only term that can yield a delta function singularity when they differentiate, because the other terms they are just differentiating with respect to x and y. No way can they give you a delta function singularity. So by singularity matching, you can say that partial z dz must be the one that's contributing to this singularity. Then you can integrate this. You can integrate this. Okay, you can integrate this across the interface. Then you can say that when I integrate across the interface, then I will have dz dc as z equal to 0 minus. And when I integrate this across the interface, I just get 1. So I have this boundary condition that the normal component of the electric flux must be equal to the surface charge density. And if I were to express it in terms of a coordinate independent form, and if I call this 1 and 2, d1, d2 must be equal to rho naught. Okay, this is the boundary condition induced by Gauss law. Okay, we can do the same thing with Ampere's law. You can do the same thing with Ampere's law. Okay, and again you can eyeball Ampere's law. It has two terms, and And assume that you have an interface and you have a current sheet, J sub S, impressed on this interface. That J sub S is going to induce a discontinuity or jump discontinuity or jump condition. Okay, jump condition at that interface. And this is finite if this has a function, a delta function singularity in it. Okay, the only thing that can produce the jump condition is the derivative of h with respect to something in the z direction. You can write that out in full, and then you will show that, or you would be able to show that n cross h1 minus h2 by matching the jump condition equal to jx, okay, equal to jx, and then you can kind of intuitively understand it because you have a current sheet. It produces a jump discontinuity. In magnetic field. So you can think intuitively that if I have a current line, a current filament, from Ampere's law, that current element produces an H like that. Now if I have a current sheet, you can think of a current sheet as being a bunch of current filament lined up together. Okay? And then if you sketch the magnetic field now, the magnetic field is going to move. Okay. It went into a strange mode. Okay, it goes back to the old mode. Okay, so what happens is that if you have this current filament line up together, then the magnetic field that it produces will look something like this. And you can see that the magnetic field n cross h across this interface is continuous. Okay, the same thing goes with the other thing that I have mentioned before, which is that for electric flux, okay, you have this thing, and what it means is that this surface charge density gives rise to a discontinuity in the normal component of the electric flux. So what it means is that if I have a charge, it has electric flux that looks like this. And if I have a whole bunch of them lined up together, okay, the electric flux is going to look something like this. If one of them produces electric flux like that, a whole bunch of them will produce electric flux like that. You can see that the normal component of the electric flux is discontinuous across this charge density. That's what it means physically. Okay, so you can repeat the same for Gauss law. You can repeat the same for Gauss law, and that would be just normal component of the flux is continuous. Okay. Okay, what about other kinds of condition where you have conductive interface? Okay, if you have conductive interface, then what kind of boundary conditions would you have? Well, I have that written out in the lecture notes, so I wouldn't belabor the point, but let me move on to something that's slightly different, which is on fields of Gauss law. So let's look at Gauss law then. Let's look at more solutions to the magnetostatic problem. Okay. For the magnetostatic problem, we have curl of H equal to J, and then we have divergence of B equal to 0, and then we say that let me fold this. Divergence of B equal to 0, then we have B equal to curl of A, and then we have Gauss law that we can derive from. Let me write it out properly. Gauss law. Okay, Gauss law is obtained by solving this equation. Curl of A equal to mu J, and as we said before, this equation can be simplified by using Coulomb's gauge. It becomes Laplacian of A equal to minus mu J. Let's assume that we have a J. J is given by a current element that looks we have a J. I don't know why it goes down to the next line. Okay, we have a J that is being carried by a piece of wire. Okay, and then along this wire we can have an element, a small current element. Let's assume that it is of length delta L, and we can draw a small element of this delta L and amplify it. And then let's assume that the cross-sectional area of this current element is delta A, and that we have a unit vector L hat pointing in the direction of the length of the wire. Then we have to solve this equation, and we already know how to solve this equation. We say that once we solve this equation, the A, the vector potential A, is given by mu over 4 pi using the Green's function dv prime j of r prime over r minus r prime. Okay? So we are going to write the fact that the current element j of r prime dv prime, which is part of this integrand, if you look at the integrand again, dv prime times j of r, it is going to be written as j of r prime delta v prime. Okay? And we can say that delta v prime is going to be written as delta A, delta L from a previous picture. Okay, delta A times delta L. Okay, and then I'm going to approximate this current density. This is current density, so it has the units of amperes per meter square. So I'm going to multiply by a unit vector pointing in the L hat direction divided by the cross-sectional area. So the unit vector is pointing in the direction of where the y is pointing. Okay, so I can write this in this manner, and hence I can write this small current element as delta A, delta L, times L hat I divided by delta A. The delta A is going to cancel each other, and then going to be left with delta L hat I. Okay. So I can actually now look at this thing and call this delta L hat or delta L bar. Okay, since it points in that direction now, I can write the contribution to the vector potential using this expression over here. Okay, the incremental vector potential that I can have from that small current element, this is only the incremental vector potential from that small current element, mu over 4 pi times J of R delta V prime over R minus R prime. And then if I express it in terms of this new thing that I have, okay, it can be written as mu over 4 pi I delta L bar. I can actually R minus R prime. I can call this prime if I want to, okay? Just coincide with that prime. And then the incremental magnetic field, which is given by curl of delta A. Remember that the curl of A is B, so curl of incremental A would be also equal to curl of B, and then that would be equal to, using this expression, mu over 4 pi and put the I on this side, and then curl of delta L prime over R minus R prime. Okay, and I can make this derivatives now. I can make this derivatives, and what you have then is that you can show that curl of L hat over R minus R prime. Okay, L is a constant, so you have this, and then you will have this being equal to L cross curl of 1 over R minus R prime. Okay, so many of you might not be familiar with how to take the curl of this complicated function. You just have to bear in mind that R minus R prime can be written in Cartesian coordinates. You're given x minus x prime square plus y minus y prime square plus z minus z prime square. Okay, so if you know how to differentiate this with respect to x, y, z, okay, this is what this means. This is differentiation with respect to x, with respect to y, with respect to z. Okay, you can go through the algebra and in fact show that this can be written as curl of this is R. Okay, this is gradient of 1 over R. This thing is equal to that. I can show that gradient of 1 over R is 1 over R squared. And then you will have a vector pointing in the R hat direction. Okay, then after you go through this complicated algebra, I'm not going to go through all the detail with you, but it is going to be quite laborious. Okay, and with this fact that this is equal to minus A cross curl of F. Okay, I make use of this identity as well. Okay, I make use of this identity to swap these two things around so that it can be written in this manner. Okay, so it's written out in detail in the lecture notes, so I wouldn't belabor the point. And what I want to say is that So what I want to say is that finally you can show that the incremental B is equal to mu I over 4 pi r square, not r square, not yet r square, dl or delta L prime cross with 1 over r square r hat, okay? And then you can also show that the incremental H field will be equal to I delta L prime over 4 pi r square crossing with r hat, okay? And putting all this together, we finally would be able to show that the magnetic field is equal to I of r prime dl prime crossing with r over 4 pi r squared. Okay, this is called Gauss Law. So the reason why I find this derivation interesting is because this was actually experimentally determined. In the beginning, in 1800s. Okay. But what is interesting is that with the knowledge that you have gained now, the knowledge about the Green's function, for instance, the knowledge of the fact that you know how to solve this equation, the knowledge that you have gained on how to solve this equation, that the vector potential can be written in this manner. So if I put an incremental current in here and go through the algebra carefully, okay, if you go through the algebra carefully, the algebra is kind of harried. If I put in the algebra and put in the incremental current element here and go through the algebra carefully, you can actually derive this Gauss Law. That is the amazing part and the wonderful part about what we have learned so far. Gauss Law can be derived with your knowledge. Okay? So any questions so far? I know it's kind of tedious. The algebra is tedious. I will rely you to read about it in the lecture notes. But the triumph is that Gauss Law can be derived with the knowledge that you have learned so far. Okay. So what about boundary condition on conductive medium? If we have a conductive medium, we have to modify Maxwell's equations accordingly. We have this Maxwell's equations for electrodynamics, and then we have this other Maxwell's equation, Ampere's law for electrodynamics. And if we have a conductive medium where J sigma E, and then in region 1, okay, we have sigma 1, sigma 2, and in region 2 we have J2 equal to sigma E2. It will be interesting to ask ourselves, what are the boundary conditions for conductive medium? We have derived the boundary condition where J is not involved as a conductor, but J is involved as the kind of an impressed current sheet. Okay, so we know that from this equation, by taking the curl and the divergence of this equation, say we take the divergence of this equation. You take the divergence of that equation, the left hand side will be 0, and you will have partial T divergence of D plus divergence of J. Okay, divergence of D is rho. Okay, we have this equation, which is the charge continuity equation. We like to ask ourselves what boundary condition would the current satisfy. Okay, again, if you were to have this as the condition, and again, if you do the fact that sorry, this should be divergence of J. And then if you put this kind of thing and say the divergence of J is equal to 0, and if you focus your attention at the interface there, it is the same as divergence of J equal to 0 when partial T equals to 0. So if you are very close to the interface, divergence of J has to be 0. Then again, you can use the argument that because of the fact that you don't have any charges at the interface, this has to be a continuous function. This has to be finite. Because this has to be finite implies that n dot J1 minus J2 must be 0 at the interface. So at the conductor interface, you have this boundary condition that n dot sigma 1 E1 minus sigma 2 E2 must be equal to 0 because J is sigma times E. Okay, so this boundary condition is kind of strange because it is that boundary condition at the conductive interface. Okay, at the interface that looks something like this. Okay, so but we have a new boundary condition sort of that we have here. Okay. Okay, we have this boundary condition that kind of contradicts this other boundary condition because previously we had derived that n dot epsilon 1 E1 minus epsilon 2 E2 must be equal to rho sub s. So, and that follows from the fact that n dot D1 minus D2 is equal to rho sub s. Okay? And we just have a new boundary condition now, n dot sigma 1 E1 minus sigma 2 E2 is equal to 0. Okay, this is conductive interface. And aren't these two in contradiction with respect to each other? Both of them are something to do with the normal component of the electric flux, but they're different. Are they compatible with each other? That's a question we like to ask ourselves. Well, they're compatible with each other as long as rho of s is not 0. Rho of s is not 0, which means that if you have two conductive media, like what you have over here, if a two conductive media, then in order for both of these boundary conditions to be satisfied, okay, there has to be charge accumulation at the interface. Otherwise, those two boundary conditions cannot be satisfied simultaneously. And this is actually what you encounter in the semiconductor medium. Semiconductor medium is often conductive, and at the interface you will have charge accumulation. You will have to have certain surface charge accumulation at the interface. Okay? So any questions so far? Okay, let's revisit what we have done so far. We started out with Maxwell's equation, and then we look at the case where partial t is equal to 0, and then these two terms go to 0, and then we have electrostatics, okay, involving electric field and electric flux only. And then from this equation we can derive Poisson's equation or Laplace equation. Okay, we have this Poisson's equation, and if you assume that epsilon is a constant, of course you can take it out and put it in over there. And then we look at the magnetostatic case. Magnetostatic case, again you set partial t equal to 0, okay? And then you just look at the equations that have something to do with magnetic field. These are the two equations that you have. Then you set B equals to curl of A, divergence of B equal to 0. Then you end up with this, what we call the vector Poisson's equation down here. Okay, vector Poisson's equation. This equation is nothing but Poisson's equation in 3 components. Okay, Poisson's equation in 3 components. You go and look at the x component, y component, z component. Each of them looks like Poisson's equation. So you can use the knowledge you have gained in solving Poisson's equation in solving this vector Poisson's equation. And we talk about the gauge. The gauge is because stipulating the curl of A is not enough to stipulate what A should be. You have to stipulate the divergence of A, and then we say that that has something to do with the fact that just like a vector, if you stipulate the cross product of this vector with another vector B, it's not enough to tell you what A should be. You have to also stipulate what the dot product of A with B should be. Then you can tell uniquely what A is. That's the essence of Coulomb's gauge. Okay, and again you can see that with this Coulomb's gauge, uniqueness is guaranteed because the phi that you have to introduce can actually be made to go to 0. Okay, if you impose the Coulomb's gauge, this phi will also go to 0, so there's no non-uniqueness problem. And then we next go over to studying boundary conditions. And then we study the case of the Poisson's equation, okay, because the charge discontinuity that you have or singularity that you have on the right hand side can only come about from the differentiation of the field on the right hand side. Differentiation of a slope discontinuous function gives you discontinuous functions. This differentiation of a step discontinuous function will give you a delta function. So if you have a delta function on the right hand side, you should have a step discontinuous function in the differentiation over here. And from that, you can actually figure out what the boundary conditions are. And then you can actually look at Poisson's equation, okay, and get the fact that the electric flux has to be something like this, and you can actually get these boundary conditions that we have. I don't know why the response time is kind of slow. Okay, you can get this kind of boundary condition. This boundary condition saying that normal flux is proportional to the charge density on the surface. You can have this physical picture to help you out with the thinking. And then we have Faraday's law. Okay, Faraday's law. Faraday's law gives you this boundary. Tangential E must be continuous. Okay, because if this is finite, the only way is that this has to be a smooth function. If it has to be a smooth function, then it has to have tangential E continuous. Okay, and then you can also look at Gauss law. Okay, Gauss law. I don't know why it responds so slowly. Okay, if you look Gauss law, okay, again, if there's a singularity at the interface here due to infinite charge density, then the boundary condition has to be the normal component of the electric flux is to be 0. And then if you look at Faraday's law, you can do the same. If there's a current singularity due to a current sheet at this interface, and then induces a current discontinuity given by this equation over here. And pictorially, you can think of that if you have a current sheet, it will produce a discontinuous magnetic field. Okay? And then we go to magnetostatics and say that now we have all the knowledge that we have about solving vector Poisson's equation. We can actually derive Gauss law. Gauss law was derived or arrived at experimentally, but with all our knowledge that we have now, you go to the math, and if you know how to swing this math, which I go into greater detail in the lecture note, you can actually derive Gauss law. So we go to the last case, which is that what happens in the case of a conductive medium interface. In the conductive medium interface, there are this current continuity equation which can be derived from Maxwell's equation because of the fact that this has to be the term with the highest singularity. Divergence of J equal to 0 means that the normal component of the electric current must be continuous. However, these two boundary conditions seem to be contradicting each other. One says that the normal flux is discontinuous but in proportional to the surface charge density. In a conductive medium, the normal component of the current must be continuous and hence equal to 0. But these two are compatible with each other as long as you have a surface charge accumulation. So what it means is that at the conductive medium interface, there has to be surface charge accumulation. So if you're in semiconductor physics, when you have two media with different conductivity, sigma 1 and sigma 2, and then epsilon 1, epsilon 2, there has to be charges, surface charge accumulation at the interface. So I'll stop here because since I'm overrunning my time. Thank you very much. Okay, I'll send you the lecture notes as well so that you can read about this in greater detail. But this is a new way of looking at boundary conditions. You will never find this way of looking at boundary conditions in any textbook. That is, you just look at the partial differential equation. You know what the boundary conditions are. Okay, I'll let you go and thank you for coming.